Alright guys, today I'm going to walk you through how to take the derivative of exponential and logarithmic functions. So this all relates to mathematical methods, units 3 and 4, focusing on area of study 3, calculus. So by the end of the video, I hope that you'll be able to know how to calculate the derivative of exponential functions, as well as logarithmic functions, and understand the general graphical intuition behind why the derivatives are the way they are. Quick aside, why bother learning about derivatives? Well, they actually have quite a few real-world applications. So for example, they can be used in kinematics, which looks at the position, velocity, and acceleration of moving objects like cars. Also, optimization problems. So you can look at minimizing cost functions, for example, as well as growth rates. So you can look at how fast a company is growing, for example. Now, quick overview. By now, I hope you're quite familiar with the derivative of polynomial functions. So polynomials are things like linear, quadratic, cubic, quartic terms, right? They normally take the form f of x equals x to the power of n. Now the derivative, a quick summary, is if you have f of x equals x to the power of n, the derivative is just nx n minus 1. So you grab the power, you throw it out front, and you decrease it by 1. If this is kind of new to you or a bit unfamiliar with it, please go and have a look through some of our previous videos. Now, I also hope you're familiar with the chain rule. So the chain rule is used when you have composite functions like f of g of x. Okay, this is also covered in previous videos. So if you're not sure what a composite function is, please go and have a look at them as well. So if you want the derivative of f of g of x, that's given by the derivative of the outside function f, and g of x stays inside, times the derivative of the inside function, g of x. Okay. Now, you might have seen the chain rule in this form, where you have dy dx equals dy du times du dx. This is the exact same thing as this, just a different notation, different form. In this case, u is just given by the inside function g of x. Okay? Now, I'm going to introduce you to the derivatives of f of x equals e to the x and g of x equals log e to the x, so exponential and log functions. Now, methods, and me as well, I'm going to focus on just exponentials and logs which have a base e, which is Euler's number or Euler's number. Okay? Now, these type of questions can pop up on paper 1 as short answers, or paper 2s as part of an extended response, application-based question. Okay, our first bit of theory. The derivative of e to the x is e to the x. So, bit of a weird thing, right? Kind of strange how a derivative of a function is the exact same function, but let's look at it graphically to kind of get a better understanding. Now, on the left, this red curve here is f of x equals e to the x. And these blue lines that I've put in are tangents to certain points on the graph. Okay? Now you should know that the gradient of a tangent to a point is the same as the derivative evaluated at that point. If this is unfamiliar, please go through some of the earlier stuff on differentiation to kind of get yourself up to speed. Okay? So what this means is that if we can look at the gradient of these tangents to figure out what the derivative is like at that point, and then we can kind of get a picture of the overall derivative graph as well. Okay? So, for small values of x, the derivative is quite small, almost 0, but slightly positive. Okay, you can see the curve is quite flat. The tangent is quite flat. Now, the reason why it's still positive is because the red curve f of x equals e to the x, that approaches 0, but does so asymptotically, which means it never actually hits 0 and becomes flat. It always gets closer and closer, which means that there's always going to be a slight slope on these tangents at low x values. Okay? Which means that the tangents will always have a very, very slight positive gradient. So what we know is that for low x, our derivative is then going to be positive but very small, close to 0. Okay. As we increase x, we notice that the tangents, they actually have a slightly greater gradient, slightly more positive. Yep. As we keep going up and up and up, we notice that the gradient actually gets bigger and bigger and bigger. The tangents become a lot steeper and an increasing rate as well. So as you get more and more in the x direction, the slope of these tangents get huge very quickly. This is actually kind of encapsulated by the graph e to the x. So we said the derivative had to be small, close to 0, but slightly positive for low x, which is shown here. As x increases, the derivative goes more and more positive and does so at an increasing rate, and eventually just gets very, very, very large. Okay? So hopefully that kind of helps you understand why graphically at least, the derivative of e to the x is actually just e to the x. Okay? Now, using the chain rule, which is written here, just for reference, if I want to deal with a more general case where I have e to the g of x, and then the derivative of e to the g of x is just e to the g of x times the derivative of g of x, which is g dash of x. Okay? Now, let's do a couple of examples. Here is that same equation put here for reference. First case, f of x equals e to the x. Well, we know just based on definition that the derivative has to be equal to e to the x. Okay? Pretty straightforward, right? Next example, f of x equals e to the 5x. Now, in this case, our g of x term is going to be equal to 5x. So the derivative of e to the 5x is going to be e to the g of x times g dash of x. So e to the 5x times the derivative of 5x, right? The derivative of 5x is just 5, so you're left with 5 e to the 5x, okay? Next example, a little bit tougher. F of x equals e to the x squared. Now in this case, our g of x is x squared, okay? So, if we want the derivative of e to the x squared, we have to do e to the g of x, so e to the x squared, times the derivative of x squared, which is given here, okay? Now the derivative of x squared is 2x, so you're left with 2x times e to the x squared, okay? Now, slightly more difficult question. F of x equals e to the x plus 1 squared. Now, if I want the derivative of this, well in this case, g of x is going to be x plus 1 squared, okay? So that means the derivative of e to the x plus 1 squared is going to be e to the x plus 1 squared times the derivative of x plus 1 squared, okay, which is shown here. Now, in order to find the derivative of x plus 1 squared, you actually have to apply chain rule. Now, I hope that you're familiar with this by now already, but if not, I'll give you a quick little summary. So, what we have to do, we have to grab the power, which is 2, throw it out front, decrease it by 1, and then times everything by the derivative of the inside term, which is x plus 1. Okay? So the derivative of x plus 1 is just 1. Yeah? So we're left with e to the x plus 1 squared times 2 times x plus 1 times 1. Okay? And if we rewrite it to make it a little bit nicer, we're left with 2x plus 1 in brackets times e to the x plus 1 squared. Okay, next bit of theory. The derivative of log e to the x is 1 on x. Okay, let's look at this graphically again. So here we have the red graph, which is log e to the x. And here again we have those tangents to certain points to indicate the slope and the derivative at those points. For small x, we notice that the tangent has a very, very steep slope, almost vertical but not quite. And again, for similar reasons as the exponential case, because the log approaches 0 asymptotically. So the slope of these tangents will approach vertical but never actually be perfectly vertical. So what this means is that for low x values, we actually have a very, very, very high derivative. Okay? As x increases, we still have a positive, pretty large derivative, but it's slightly less, right? Because the slope is slightly less steep, yeah? As we keep increasing, it gets less and less and less steep. Still positive, but less and less steep until it approaches 0. It doesn't actually ever hit 0, but it approaches 0, okay? This is shown with the graph f of x equals x plus 1, f of x equals 1 on x. So we can see that for low x, we have very large values. And as we increase x, we decrease our value as we approach 0. Okay? So that means the derivative of f of x equals log ex is 1 on x. Now, if you know what 1 of x looks like, you know that it actually has a negative component down here in the quadrant 3. This is not the case for this graph because log e to the x only has valid values for x greater than 0. Okay? Which means that the derivative can only have valid values for x greater than 0 as well. Okay? Now, using the chain rule again, if we have d dx of f of g of x, that'll give us f dash of g of x times g dash of x, we can kind of get a bit more general expression for the derivative of log e g of x, which is g dash of x divided by g of x. Okay? Now this is all provided g of x greater than 0. Now what I mean by that, if for example this g of x term, if it could output negative values, so let's say if I plugged in x equals 0 into g, I got negative 1. Then I would have to take log e of negative 1. And you can see on the graph of log e dx here, right, that you can't input negative x values, only positive. What that would mean is that if you tried to input negative 1, you would get undefined, which is not good. So this thing only applies when g of x outputs values that are strictly greater than 0. Okay? This is some worked examples. So here is that same equation written here. Let's look at this example. So this is a pretty straightforward one. By definition, we know that if we have f of x equals log ex, the derivative is just 1 on x. Okay. Let's look at f of x equals log e 5x. Well, in this case, our g of x is 5x. So we found the derivative of log e 5x is just g dash of x, so the derivative of 5x divided by 5x. Yeah? The derivative of 5x is just 5, so we're left with 5 on 5x, which actually simplifies to 1 on x. What this shows us is that in some cases, having a little number here which scales the x doesn't actually change the derivative, which is interesting. Now, next example, f of x equals log e x squared. Now, in this case, g of x is x squared. So the derivative of log e x squared is going to be the derivative of x squared divided by x squared, just shown here. Now, the derivative of x squared is just 2x. So we're left with 2x on x squared, which actually simplifies to 2 divided by x. Okay? So, last example. F of x equals log e x plus 1 squared. In this case, g of x equals x plus 1 squared. Right? So the derivative of log e x plus 1 squared is going to be the derivative of x plus 1 squared divided by x plus 1 squared. Now, like in the previous case with exponentials, the derivative of x plus 1 squared actually needs to use chain rule. And again, it's shown here. Quick reminder, you grab the power, you throw it out front, and you decrease it by 1, and you times the output by the derivative of the inside, which is, in this case, is just 1. Okay? So, we're left with 1 divided by x plus 1 squared, times 2 times x plus 1 times 1. Now, after a bit of simplification, you notice that this x plus 1 term actually cancels out with one of these x plus 1 terms. So your final answer is 2 divided by x plus 1. Now, final remarks from me and tips is just for you to practice as much as you can. Practice is very important when it comes to methods in general. If you find this stuff quite difficult or unfamiliar, the more you practice, the more confident and comfortable you will get. Okay? Now, if you are struggling early on, it might be useful, for example, in these cases, to strictly define what g of x is. So, for example, here, say g of x equals 5x. Write that down if it helps. And then do these steps individually. Okay? Now, I would recommend not trying to skip steps early on unless you're very comfortable doing so. Again, if you do this quite early on, you're going to open the door for little bits of error to kind of slide in there and mess up your final answer. So, as you practice and get better and better, then I'd recommend you automatically will start being a little more comfortable when it comes to skipping steps. Okay? Now, if you're having trouble with this, don't stress too much. Okay? If you just keep on spending some time and practicing, I'm sure that over time you'll get a lot more comfortable. It'll make a lot more sense to you. All right? Thanks, guys.